Okay, hi everyone. So I am Nicolas Milojevic-Dupont, a PhD candidate at MC Berlin, and I will be moderating this next session on machine learning for sustainable and resilient built infrastructure in urban areas. So yeah, the built infrastructure is a critical component of climate policies, both because of the large energy use of buildings in cities, as we just heard in the previous session, and because also of the vulnerability of built environment to extreme weather events, and as we could also hear in previous session, access to good data in the built environment can be a bottleneck, a real bottleneck in designing effective policies. So we'll discuss now how machine learning can help generate data on infrastructure with remote sensing, in particular in low-income countries, and how machine learning can help upscale building energy use modeling at the city level. So we'll have 4 short talks and some time for discussion after. And so, yeah, if you have questions or discussion points, please post them in the chat, and we'll call out your name and unmute you to ask the question. And if you would like us to read out the question instead, please indicate that in the message. So our four speakers, present the 4 speakers now. We have Monika Kuffer, who will start, and who is the assistant professor at the Faculty of Geoinformation Science and Earth Observation at the University of Twente. A main research focus are urban remote sensing, monitoring deprived areas, and analyzing urban form and dynamics with remote sensing, spatial statistics, and spatial metrics. And our research is driven by providing spatial information to support planning and decision-making processes in complex cities toward inclusive, livable, and sustainable cities. Then we'll have Nick Jones, who is data science lead at the World Bank's Global Facility for Disaster Reduction and Recovery. Nick is an urban development specialist with more than 15 years experience in public policy roles, and it focuses on scaling up the contribution of data science and machine learning to urban development and resilience. And we are very happy to have Nick again after his last intervention with us at MLD 2020 in Lausanne. Third, we'll have Alex Nutkiewicz, who is a PhD student in the Urban Informatics Labs in the Department of Civil and Environmental Engineering at Stanford University. And research focuses on ways to leverage urban data streams to improve the energy performance of buildings in cities. Some of the projects are using neural networks to predict the energy consumption of buildings at different spatial temporal scales, analyzing the impact of energy efficiency retrofit on urban buildings, and understanding of various building design parameters affect thermal comfort in informal settlements. And last, we'll have Sokratis Papadopoulos, who is a PhD candidate in urban systems and informatics at New York University, and a researcher in the Urban Intelligence Lab at NYU Center for Urban Science plus Progress. And his recent projects leverage machine learning algorithms to identify patterns in urban energy consumption, develop robust and fair city energy performance metrics, and assess the effectiveness of existing climate action policy frameworks, among others. So Monika, if you want to share your screen now, you can start.
Good. Hi. I hope you can see my screen now.
Yes.
Yes, great. Hi, I'm Monika Kuffer from ITC University of Twente. And I will give you a short presentation about global urban data gaps, and with a very strong focus to the global south, and a very strong focus on how machine learning and Earth observation can fill some of the data gaps, particularly of what I call deprived typically known as slums, urban poor communities, etc., where the data gaps are even worse as compared to the rest of the city. So what you see typically on global urban data sets is that they're often of very coarse resolution, very coarse, which has to do with the fact that they're working with moderate resolution images, as high cost images are very intensive, but also processing intensive. You see an example of the city of Kampala in a fantastic global data set, but also you see the limitations of this global data set, like the global human settlement layer, which maps on the whole globe build-up areas. But you see for the city of Kampala, if you want to use this now in the context on the SDGs, like SDG on urban open spaces, that it's very coarse and it doesn't really show the open spaces in cities. So what you see on the right side of the slide is that you have been experimenting with also low cost or free cost data for researchers like rapid eye images to bring the resolution to get a bit less cost resolution data sets for cities in the global south to be better able to access the amount of open spaces and the loss of open spaces using cloud computation. Another example of open, oops, sorry, wrong direction. Another example of huge data gaps, and now typically focusing on deprived areas, on slums, is the example of SDG goal 11.1.1 indicator, where we see that the global data, they don't have any information about the spatial dimension where slums are located. They often have huge data gaps, like you see. I know how good the slides are now shown because of the setup with Windows. Is that we have been observing in cities in India, for example, that half of the slums are not part of the official data sets on slums. So they're typically forgotten, they're not mapped, they're not recorded. That's an example you see on the right is the city of Mumbai and a slum which maybe some of you know, the slum of Dharavi, one of the biggest global slums. And what you see that the census is recording for this whole yellow area, which is the census boundary. It's recording about 450,000 people living in this ward. But inside this ward, a much smaller area is the slum of Dharavi, which locally, it's relatively confirmed that about 800 to 1 million people live in this area. So you see that there are huge data gaps in official data. And typically what you observe in all the data layers, also the really very, very interesting data layers like the world pop maps, is that they are really very poorly performing in urban areas and very much poorly performing in the global south, and typically not performing at all very well in the areas where the poor communities are located. Why such data are really important to have? It has many dimensions. Like, for example, I'm working a lot together with colleagues from the health community, from health researchers. So if you want to plan a health survey, you need to take typically a sample. If you now take the city of Nairobi, where about 60% of the population lives in about 4% of the build-up area, and if you take a random sample, you typically will miss out most of the poor communities. So you don't get data on this group of people, which is very much in need of being seen and also being understood how, for example, life expectancy differs between the better off area and the poorer communities. Also another case, also linking to this session, is in the case of climate change and disasters happening. Typically, if a disaster happening and a poor community is destroyed, people don't have any evidences on their existence. So they typically drop out of any compensation schemes if in a recovery phase. So data on such areas is urgently needed, but it's not existing in any global data sets. That's also one of the limitations we encountered in one initiative together with UN Habitat. We have been starting last year on building the climate resilience of the urban poor. And the first focus was to map the +100 most severe hotspots threatened by climate change. And it was like a data exercise which was really eye-opening for us, because you don't have any data to support this exercise. You don't have data showing the location of poor communities. Global layers on climate change vulnerabilities are very coarse. So what you see is the example of the city of Mumbai. If you take global data layer, like again, the global human settlement layer, it doesn't give you any idea about the location of the urban poor. We have been generating a global data, city level data set on the location of the urban poor. And what you see is that the slum communities, they are typically located in the very low-lying areas of the city as compared to the rest of the city. Why you have such global data gaps? Maybe this list can be much more extended, but there are many complicated issues to be addressed, like really having a good understanding of the local context, what makes such area different from others. That's an example. And typically you need this type of training data to train deep learning algorithms. It's an example that we ask local experts to delineate for us the location of the slums in the city of Jakarta. And you see that only in one area, the 5 experts agreed on the location. All others, for other areas, there's a high level of uncertainty of the location. But often what you see, models are trained without even having any local context. There's an important issue also to further develop methods is to go to methods which are scalable and transferable and are not limited by the high costs of high resolution images, which can go to up to more than 20 euros per square kilometer. So you can imagine that a global data set wouldn't be feasible at that cost. We also see that if you want to use data, local data, they have large data gaps. And then the major question is also going towards aggregations, at what aggregation level such data should be produced, how should they validate it, and also the question of ethics. So how should data be provided, not violating privacy, and also not maybe making communities even more vulnerable in terms of potential evictions and other discriminations. A project we have been starting with, which is focusing on sub-Saharan Africa, is developing open source and low-cost solution for mapping slums in sub-Saharan African cities. We have been starting in the moment with 3 cities, Burkina Faso, Nairobi, and Kisumu. But also what we are thinking about is very much not going to this very binary vision of deprived, non-deprived, slum, non-slum area, but seeing this area not as a very unique group. In the picture you see examples of what are locally labeled as slums in an Indian city, in the city of Bangalore. And you see that these areas differ dramatic from upgraded areas to very poor, very temporary settlements. And we have been trying to see, can we use a deep learning method to predict their differences across the city? And we could train a model to predict the differences with around 75% of R square. And that's also goes to an initiative going to looking to and bring slum mapping experts together. What we see that a lot of the experts and mapping experts, both from the Earth observation community, but also from the community mapping field, that we all work as individual projects. And this idea is to bringing a network together to build an integrated deprivation area mapping system, addressing many of the global challenges and also data gaps in combining the efforts. And that's already, I've promised to be short. My last slide, so what we see is that we need to bring much more the spatial dimension of deprivation and add this to global maps, because it's an important data layer for all contexts to understand vulnerabilities, resilience, health outcomes. which we also see in the moment with COVID-19 outbreak, that particularly urban poor communities are particularly affected. There are huge data gaps to organize help. My colleagues from Slums International, they're doing it on the ground in the moment fantastic work, which are also part of the Idea Map network. And yeah, it's an open invitation to join Idea Map for those who are interested in this field. Thanks a lot. I hope I didn't take too much time.
Yeah, thank you very much, Monika, for the amazing presentation. Now you can unshare your screen, and Nick, you can share your screen. And so now we will have Alex. You can share your screen, Alex.
Great, thank you. Okay. Awesome, can everyone see my screen?
I can.
Sweet, okay. Let me just get this going. Great, so hi everyone, and hello from my quarantine department here in San Francisco. As I was nicely introduced, my name is Alex Nutkiewicz. I'm a PhD candidate at Stanford in the Urban Informatics Lab, and I'm really excited to have been asked to talk about some of the ideas that inspire some of my PhD. So as a lot of you probably already know, the world is rapidly urbanizing. Cities are currently home to over half of the world's population, and that number is expected to balloon to over 2/3 by 2050. And this will require the creation and expansion of hundreds of areas across the world. And so in addition into taking on significant increases in population, cities are now also instituting ambitious greenhouse gas emissions targets that are aimed at limiting the severity of global warming. So for example, my home here in San Francisco is aiming to reduce about 80% of its emissions from 1990 levels by 2050, while still needing to provide the same amount of services to what will be an even greater number of residents. And so a prime place to do this is in the building sector, which accounts for about 40% of all primary energy consumption. So there's this great opportunity for urban planners, engineers, designers, and policymakers to collaborate on new tools to better inform urban planning and policy, just to better improve urban energy efficiency. And so that quite broadly is the objective of a lot of my research for my PhD. So I want to talk a bit about how we go about evaluating urban building energy consumption on a building detailed level. So the way we primarily do it is through a physics-based modeling tool called a building energy model. It takes hundreds of inputs about a building's constructions, operating schedules, and energy use dynamics in order to predict energy consumption at a building level. Here's the problem. So while they are able to get a pretty good understanding for what factors influence a building's energy use, it's often unable to consider the influence of the buildings around it, what I like to call the urban context. These models can't really consider things like urban heat transfer or shading, or even complex urban environmental concepts like the urban heat island effect. And so when you couple all of these urban contextual effects on building energy use, it can result in extremely inaccurate predictions of energy use on the urban scale. And that can result in severe energy emissions and economic consequences for stakeholders involved in the urban built environment. So luckily, and what I think is going to drive a lot of the conversation we have during this session, is that rapid growth in sensing technologies and emerging smart city initiatives are allowing us to harness the explosion of structured and unstructured data streams that describe the urban built environment. And while there are so many emerging data-driven ML, AI models that can leverage this data to predict building energy use on a pretty accurate scale, we should still be ensuring that the tools that we're developing for policymakers, urban planners, and building energy designers still remain interpretable despite maybe not having as deep of a software background. And so while traditional physics-based modeling and newer machine learning models are often treated as two very separate fields, I believe these approaches are actually very complementary to one another. So physically based representations of buildings are interpretable, they demonstrate the underlying drivers of building energy use, and they also allow us to extrapolate what might happen to buildings under future energy scenarios. So if a building goes through a retrofit, a physics-based building energy model can still tell us what will happen to that building in the future. On the other hand, a data-driven approach is really great in uncovering hidden temporal patterns in energy data, for example. And so by integrating these two types of methods, we can better understand some of the complex spatial temporal dynamics of building energy use. So the key idea behind a lot of my research in my PhD is to develop this urban scale energy prediction model that integrates this traditional physically based energy modeling with more complex emerging data-driven deep learning modeling to better capture some of the spatial temporal nuances of urban building energy use. And so far in my work, I've been able to understand and capture the urban energy consumption of buildings in a couple cities within California. And some of my ongoing work, which hopefully will be published soon, is looking at understanding how urban scale retrofits, so retrofits that occur in several buildings across the city, not only influence the buildings that are being modified, but how they affect the ones around it as well. So that's essentially my work in a nutshell. I'm really looking forward to the Q&A session where we can have a bit more of a deep dive into some of these topics. But thank you for listening. And yeah, that's it.
Thanks a lot, Alex. Very good talk and amazing slides.
Thank you.
And now we have Sokratis. You can share your screen.
For some reason, it doesn't allow me to share, I think. Let's see.
Oh. Shoot. Yeah, I don't know why.
Oh.
You can.
Do you mind if I share like a link with you and you guide?
Yes, yes, and I can share them. Okay. Okay.
You got it?
I got it, and now.
To take some time, we can ask a question in between. What do you think?
Yes. Yeah, you can. Yeah, you can go ahead, Konstantin. Maybe.
Okay. We'll ask. Okay, let me go to the top of the questions. The first question we got is for both Monika and Nick, I think. What is the percentage of useful data that you use that is freely available, including Earth observation data? And is the growing commercialization of data an obstacle to providing better maps, especially to poor and vulnerable areas? So feel free to answer either Monika or Nick.
I'll quickly start. Yes, I very much share this this problem, and Honestly, many of the studies we are doing are with commercial data, which we try to get at least for research via data grants. So we typically don't buy data. But in a moment we are working very much on experiments with sentinel images and to see how far can we get with sentinel images on, particularly if you want to upscale it to some global mapping product. I think the way forward is to work either with very low cost or with free cost imagery.
All right. Are we ready with the presentation, or should we ask another question?
You can go for another one.
All right, I'll go for another question then. Let me see.
Sorry, guys, I think I figured it out. So maybe
You figured out?
I think so. Yeah, it was just a matter of permissions.
Oh,
Yeah.
perfect. So can you try it out now? Oh, very good. It works. All right.
Beautiful.
Can you all see my screen?
Yes.
Okay, perfect. So, hi everyone. I'm Sokratis. I got my PhD from NYU in urban informatics, and today I'm going to be presenting to you part of my work on how to leverage energy disclosure data and machine learning algorithms to fight climate change, and more specifically on how we can use these sources to create the next generation of energy performance grading for buildings. Before I dive into the presentation, I want to start by stressing the importance of cities taking action about climate change, with New York being in the forefront of it, spearheading these efforts with a very aggressive plan to reduce its carbon footprint by 80% by the year 2050. And as part of this roadmap, what the city executives did is to launch an energy disclosure law that mandates all properties with square footage more than 50,000 square feet to annually report their energy usage. So why this is important for us as researchers or data professionals is that we now have access to unprecedented data streams that we can use to benchmark energy consumption, establish peer-to-peer comparisons, and monitor trends over time. Fast forward to today, 10 years after, New York is going even more aggressively with its climate action plan. And what they're introducing this year is a public display of energy grades. So for those one of you that you have visited New York, most likely you have seen something like the picture on the right, the letter grades on the restaurant cleanliness. So we should be expecting something very similar to appear in the front doors of buildings starting this year. However, the issue with this, there's an issue with this approach on the way these grades are being calculated, and this is what I'm going to be talking most in the next slides. So the method that New York City adopted for this energy performance grading is based on Energy Star, which is the state-of-the-art model, is the most well-known energy benchmarking model in the US at least. And how their algorithm works very, very quickly is that they collect data from 322 residential buildings. They use this data to build a linear regression model to predict energy use intensity. And then after having the model predictions and the actual EUI, they're computing these energy efficiency ratios that they plot then you get the cumulative distribution of that. You fit a curve, and then after binning this curve in 100 buckets, you having your 0 to 100 energy score scale. Let me spend some time now identifying the flaws of this approach and proposing some solutions going forward. So first and foremost, there is a fundamental issue with the model specification. It is very clear in the energy research that the drivers of energy consumption is oftentimes complex and highly nonlinear, the relationship between the two. Therefore, we argue that a linear model is not enough, and we should we should go for more advanced machine learning algorithms to tackle this problem. Also, there are some findings that the continuous scale, the 0 to 100 scale of Energy Star, is not really intuitive for the end users to adopt. And therefore, we're suggesting that it would make more sense to use unsupervised learning to cluster these energy performance ratios I mentioned earlier to inform a letter grade system. Now, moving on, how energy disclosure policies can provide us with the data to build better models around energy performance. First, we're moving from a nationwide standard to city-specific data that are collected in the city level, which are more contextualized and are able to capture the within-city heterogeneities of the buildings. Also, we're moving from small data sets, I mentioned, around 300 buildings in the Energy Star model, to a sample of more than 7,000 residential buildings in New York only. And also, the other benefit with energy disclosure policies is that they're coming with a plethora of physical and operational characteristics about the building that we can use as inputs to our model to make them more robust and more accurate. And with this in mind, we created our own city-specific energy performance grading system. The machine learning pipeline behind it is quite straightforward. We're starting by cleaning the raw data, removing some outliers and erroneous values, and doing some feature engineering. Following, we're using a XGBoost algorithm, which we fine-tune its parameters through cross-validation and then train our prediction model. And finally, after we have the model trained, we calculate the energy performance ratios similar to the Energy Star approach, and using k-means clustering to form them into letter grades. And here's where we're comparing the performance of our approach and the Energy Star. We see that it's very clear that the city-specific approach outperforms the Energy Star model. And not only that, we see that Energy Star fails to explain any of the variance in the city, any of the variance in the New York City buildings, which raises the question whether this is a useful model whatsoever. Next, we show how we use k-means to cluster the data, and on the right, we contrast the Energy Star-based grades that were adopted by the city of New York versus our approach, and we see that there is a discrepancy of approximately 40% of New York City residential buildings are going to be assigned into a different category under the two schemes. And before I conclude this presentation, I want to talk a little bit about the implication that machine learning algorithms and energy disclosure data can have on climate action policy. First, with tools like the one I discussed, we are able to provide the tools needed for evidence-based decision making, and this can go both top-down and bottom-up. From the top-down perspective, we enable policymakers to make more data-driven policy decisions, whereas on the bottom-up, we expose landlords in more peer pressure and also enable tenants make more informed real estate decisions. Now, an additional implication of energy disclosure data is that they can help decentralize energy efficiency efforts. We can come up with market-specific solutions. Every city can come with their own set of tools, learn from each other, and it allows for a lot of opportunity to foster innovation. And this is it. Thank you very much.